So today we talked about one more force that is of importance, and then we talked about, started talking about energy, we started talking about work. But the force that we talked about was the force of friction. And there were two different cases, because there are two different types of friction. There's static friction when the object is not moving, and there's kinetic friction when the object actually is moving. So we call the static friction force small f sub s. That's when the object is not moving. So, say you have a box on the ground, and you're pushing on it and trying to get it to move. It has a contact force with the ground preventing it from moving based on what type of material that ground is made of and what type of material your box is made of. And the static friction will build as a number up until a maximum value when you can finally push it and make it move. So Fs max is the maximum value of that force. And so if you exert a force on whatever situation is going on, bigger than this force, then the object is going to move. Okay? And then it becomes kinetic friction, which we call F sub k, because the object will still be in contact with the ground, but will now be moving. And we quantify these things by a coefficient of static friction and a coefficient of kinetic friction, u sub s and u sub k, which are different numbers based on your surface. So snow will have a different coefficient of static friction or kinetic friction than, say, sandpaper, then will glass, then will concrete, then will anything. And so you need to know that, or you can figure it out based on other things in the problem, but that is a necessary thing. And it turns out that these things are related through the normal force, meaning how much the object is pushing into the ground, or whatever surface you're talking about, and therefore the reactive force that that ground or surface is experiencing because of the weight that it is feeling. Okay. So the more it's pushing into the ground, the higher the normal force is pushing up, the greater the friction force. And so the plain old static friction force will be less than or equal to the mu s times n. So the max value of this is going to be equal to your coefficient of static friction times your normal force. Again, the bigger the normal force, the bigger your friction is going to be. Okay, because you are in that surface. I mean, you are in contact with that surface. So even if you have your hands, as I'm doing right now, and move them back and forth on top of each other, okay, there's some friction going on between your two palms. If you push them together, it's harder for it to move, and your hands heat up faster because of the friction that's there. And the friction increases because the normal force has increased, because you've increased the forces that are acting there. So Fk is equal to mu sub k times n. And then of course that means that in all the other things that we've been analyzing, like inclined planes or pulleys where things falling off ledges, or just somebody pushing something on the surface, that now you have a net force that has to involve your friction. And of course friction is a very important force, otherwise we couldn't walk, we couldn't grip anything, we couldn't move around, we couldn't do anything, because we need to have that sort of phenomenon happening in order to do that. Otherwise you can't. Okay, so that was the force of friction. Now, also I should mention about direction of the force of friction, that it always acts to resist the motion. So if you are pushing a box, and you're going in this direction, your force you're applying is to the right, but the friction force between you and the ground will be moving to the left. And if this box is actually moving, then it's going to be the kinetic friction that's going to the left. So if you're applying a force which we'll call, well, I'll just call it F. and I can't think of any other letter to give it right now, then the net force on the box would be equal to your force that you're giving it in the positive direction minus the kinetic friction force to equal the actual acceleration the box is experiencing, which would be toward the right, assuming that you're moving it to the right. And so I put the positive there on top of the acceleration. Because Newton's second law tells us that the sum of the forces is equal to the mass times acceleration. Or everything that is causing the behavior, all those net forces together, equals the effect on the object, or therefore the object's behavior. So the cause equals the effect. The cause being the forces, the effect being the behavior the object is experiencing, the acceleration that it experiences. So the sum of these two forces, the positive F and the negative friction, is going to give you the acceleration of the box towards the right. Okay. So then the next part we talked about was the idea of work, which is different. We're moving on to chapter 5 now with energy. And the idea of work is different from our idea of work and toil that we have in the everyday world. But for work, you're talking about the energy expended by or done by, well, say energy expended. The energy expended by a force acting on an object through a distance, through a specific displacement. Acting on an object through a displacement. And the tricky thing about work and this definition is that only the force directed along the axis of displacement matters. So, if I do have the same situation where I have me pushing the box, or you pushing the box, okay, and you're moving it this way, you're doing work in the x direction. No work is being done in the y direction because delta y is going to be 0. There's no displacement from the ground. Okay? And if you lift it up and then put it back down, no work has been done because your delta y is 0 through that time span. Okay? If you lift it up, you've done work on it. And if you put it down, work has been done on it. The work you do going up is positive. The work you do putting it down is actually negative, because the force and the displacement are in different directions. So let me address that. So for work, let me erase this picture for a second. Work is equal to the applied force on an object times the displacement of the object in some direction, we'll call it x for right now, times the cosine of the angle between the force and the displacement. So in that same idea with the box, if I am pushing this box to the right, I have some force I'm pushing it with. I'm going to be pushing it through some delta x, from some starting point to some finishing point, and the angle between my force and the direction is 0 degrees. So that cosine of 0 is positive 1, so my work would just be the applied force that I am acting on it times the displacement. So, in the last thing I talked about friction, there's a friction force that this box is experiencing. So I'm pushing it to the right, but there's a friction force that's acting to the left. The friction force is also doing work on the box, but the angle between the box and the friction force is 180 degrees, because the displacement's going this way, and the friction force is pointed back, so the angle between my hands right there is 180 degrees. So that would be negative. So this work would be, so the work done by me on the box is equal to my work, I'll say F sub me, times the displacement, times the cosine of 0 degrees. And then the work done by the friction will be the friction force, because that's the force doing the work in that question, times delta x, times the cosine of 180 degrees, which is -1. And so the net work that the box is experiencing would be this one plus this one. So we have a positive work going to the right, a negative work going to the left. When you add those together, because the box is moving to the right, you should end up with a positive work going in that direction. Okay, so it really does matter only in the parallel direction with regard to the displacement. And when I say it, I mean the force. So any force in the same direction as displacement will do work. Okay. So if I am instead pushing at an angle on this box, like say I'm pushing down on the box as I push it, okay, and this is the force, and I'm making an angle of, say, 15 degrees right here, okay, and it's moving in the delta x, not the delta y. Well, now you have the F that you're applying, F sub me, times the delta x, displacement it's going, times cosine of the 15 degrees, because that's the angle between the force you're applying and the direction. Okay, it's not the angle relative to some ground or some vertical, it's the angle relative to the actual displacement. It is the angle between the two actual things, the force you're applying and the displacement that it is going. Okay. So yes, there is a force that you are acting in the y direction, but all that is doing is will increase the weight force the box experiences, which actually will increase the normal force pushing up, which increases the friction force that is there between the box and the ground. Okay. So it will take a bit of time to get used to the idea of work, but that is the idea right there. So the force of gravity acting on this box has an actual work of 0, because delta y is 0. Okay, and also, the angle between gravity and the displacement is 90 degrees. So cosine of 90 is 0. So it has 0 times 0, which is definitely 0. And one more thing to mention, which I mentioned at the end of class, friction is a dissipative force, or dissipative force, meaning that it takes energy away from the system. And we'll talk about why that is important when we talk about conservative versus non-conservative forces, to see what forces conserve the energy and where the energy goes if it's not conserved in the confined system. Okay, but first we're going to deal with this idea of work, which is in units of joules, or Newton meters, and those are the same units as energy. So that's why we need to talk about work with regard to energy. We'll be talking about more of that on Thursday.